Hey everyone, thank you for coming to my talk for sshlogin, securely authenticated to remote Linux systems via serial or text-based interface. I know the title is quite long, but it's quite a niche case with specific challenges, so that's why I wanted to present to you this today. A little bit about myself. I do Linux at Cloudflare. Anyone here who doesn't know about Cloudflare? Why is laughing? Since recently everyone knows about Cloudflare, right? I do system security and performance, and I enjoy low-level programming. So Linux kernel, device drivers, bootloaders, and other stuff written in unsafe programming languages. So I'm a die-hard Linux fan. That's why I'm presenting from a Mac today, because I know too much about Linux to be presenting it on the conference. Okay, but anyway, so let's talk about remote system access. Who here manages some kind of remote infrastructure like devices, servers, VMs? What do you use for remote access? Right? I try to summarize, right? It's probably one of these three, either SSH, VNC, or for Windows, mostly remote desktop. And these are good protocols. They're kind of like state of the art if you use the latest versions. So, they use they're like secure cryptographic protocols underneath. So it's always some kind of public key based cryptography. You have full session end-to-end encryption. And most of them have hardware key support, so you can have hardware security embedded in your flow. The good thing about these are no shared credentials between users of the system. There are no secret rotations, so everything is ephemeral. Every authentication session is ephemeral, so the protocols are designed in a way that the way how you interact, everything you have a one-time key, one-time authentication, and everything. If within the protocol something leaks online, people cannot use it for bad things. What are the downsides of these? Can someone name one downside? Well, they can if they're old, but ideally, the biggest downside, they require network, right? Communication. The whole point when you build the secure networking protocol, they're complicated. There is a lot of packet exchanges coming going, and it's also the case with TLS. There is a handshake, which sends a lot of information back and forth just to establish a shared credential. So you always require some network access and some bandwidth to do it. What about if your machine is broken and you don't have network access, right? So happens from time to time. And it's not sometimes it's not the network is broken. Sometimes when you manage remote servers, you can misconfigure a machine and you lose access. So the IP address is not there, so you cannot connect it and recover it. So how do you remotely recover such machines, right? So how do you remotely access machines with no network? Well, finally, you still need network to access machines remotely, right? So you have some kind of usually an emergency secondary network. We call it OB, out-of-band network. For server infrastructure, it can be a dedicated network, for example, it can be a provision network. It can be, for example, in data centers, you can have backup connectivity via mobile devices, right? My SIM cards or something like that. It can be your primary network if, for example, your server has no network connectivity, not because of the network problems, but because it was misconfigured. But you still need to remotely connect and somehow recover it, right? But because you cannot to the server directly, you need a dedicated device, and usually you have something like a KVM or BMC. So KVM is more for client and embedded machine world, where it's a real dedicated device which is wired to your primary machine. In server world, most of the time you have a thing called BMC, which is a small computer, separate computer embedded into your server chassis. So even though it's within the case, it's still a dedicated machine and somehow connected to your primary machine, which can kind of recover it. But regardless if you have the KVM or BMC, the way how you control machine is different, right? So all that these devices provide to you is when you connect to them remotely, somehow to control either the primary machine's KVM is like keyboard, video, mouse, so it kind of streams the monitor, and it allows you to kind of like virtually control the mouse or the keyboard of the remote machine. Or if you have just a serial text interface, it can also like forward a serial port, for example, like which is mostly used. Yeah, it's like RS-232 serial port through the KVM stream through the OOB. But how does it look like? Even though there are two different cases, from a user's perspective, you have this, like, the only interface you have to a machine to log in is a screen with text on it, right? So you can only read what is presented to you on the screen, and you can type the response. So the only way how you can interact with the machine is by reading and typing. So you cannot like stuff a good networking protocol on top, right? So, and this is why we're investigating a problem of emergency access. So because when we have only reading and typing capability. And in many cases, this is the weakest link in the system, right? Because you can design as secure protocols for normal access as you want, but while you have this, like an attacker can use it somehow to get access into your system. And usually for emergency access, it's very often overlooked into like accessing security postures as well. So the big question here we're trying to solve is, can we have a modern secure authentication scheme over a text-based interface where you can only see and type? Okay, clear? And the modern way to basically interact with it is usually still the password authentication, and we want to move away from it. Who still uses passwords for logging in to remote systems? Yeah, so why passwords are bad? That's a quick recap. We probably know that, but well, if you use password, passwords have to have enough entropy, right? So normally we don't come up with passwords ourselves these days. We generate them randomly and store with the password manager. But yeah, like if you have a weak password, people can kind of try to guess it and get into your system, right? So passwords, we need to somehow ensure that passwords have enough entropy. Well, passwords also like make offline attacks possible. For example, if I somehow manage to steal your server's etc shadow file, right? I have all the password hashes, and I kind of try to apply like a dictionary attack on top to recover these passwords. Like if you didn't have enough entropy, I can probably do some kind of like brute forcing attack, right? So I can recover the password even without access to the server. Like bonus point, where is this GIF coming from? Which movie? Huh? No? Everyone says hackers, like it's Terminator 2. So yeah, passwords are prone to leak. Thank you, AI, for helping me to generate this image. Yeah, so we have the schema, right, of communication. Where do you think password could leak here? Any ideas? The answer is everywhere, right? Like anywhere. So it's less likely to leak on the emergency out-of-band network if you have a good setup, because ideally, at least here, it's a network access, and you can set up an end-to-end encrypted channel to the KVM or BNC. But it also depends, right? Because these are kind of embedded-like devices. They're usually run older software and like have more vulnerabilities in them, and they might just not support modern protocols. But like in the best case, you can still have an end-to-end encryption, so less likely to leak in the emergency network. But again, it can leak from the BMC device itself if it has vulnerabilities, it can have malware, and the rest of the connection is not encrypted, right? So like somebody can sniff the serial port for your password, and somebody can have malware on your server as well to kind of like get it. The other problem, like if you're managing a big infrastructure, is that what we had is shared passwords. So Obviously, we have a group of people, like SREs, managing remote infrastructure, and everyone needs to be able to log in as root. Therefore, the root password used to be shared between those groups, right? And the problem with when you manage a shared password in a group becomes like, how do you do revocation? So in a normal case, if you need to revoke a password, so let's say someone leaves the group, they move out of the SRE organization or even out of the company, what you need to do, it is very cumbersome. You need to create and release a new operating system image, and then like they distribute the new password for the new image to the remaining group. In practice, it's very hard because like we cannot reboot all Cloudflare at the same time to the new image, so we like do it slowly one by one. Eventually, in our infrastructure, we have like machines running different images. Some have a new password, some have an old password, which means the revoked entity still can access some of the infrastructure. And the legitimate users now have a user experience regression because when they connect via emergency console, they kind of don't know is it a new or an old version, which password they should try, right? So, and most likely, if it's an emergency access, that server hasn't been online for a while because it's broken, therefore it runs an older image. So you need to have this guesswork. And like if for some reason you need to do an image rollback because of the other regression, you can unrevoke the password again. So not great. So what could we do for password alternative authentication for a text-based interface? Well, we can do like OTPs or one-time passwords. Who used OTPs at some point? Right? Everyone probably through Authenticator app. So, but in a nutshell, how OTPs work, you have this setup phase. And basically before your server loses connectivity, you do the provisioning phase, you provision an OTP seed, which is essentially a shared secret between the user, which will then later authenticate, and the server itself. And there are different variations of OTP. The most common that we probably use with Authenticator is time-based OTP. So now this initial state, both server and the client, they know that's shared secret, but we need to prove to the server that we know the secret without actually revealing the secret in a one-time manner. So with time-based OTP, what we use is some kind of a message authentication code, like most commonly HMAC, and we kind of like use our secret and hash it with the current time and produce a result like an OTP. So we can present this to the server, and the server can kind of do the same thing and check if the server arrived to the same conclusion, and it's only possible if you use the same inputs, right? So if the shared secret is the same, so the server can authenticate you. So the good thing about this is it's kind of self-contained, and in one way, user experience is very similar to password. Instead of just entering the password, you go to Authenticator and type what it shows you, but that keeps changing all the time. The problem with this is like it requires both parties to have time in sync, which is kind of like, by definition, if that has no network, like it's quite hard to achieve. Like if that out of sync, the time-based OTP is not work. And also like the time-based OTP is not truly an OTP, so the password is valid not one time, but in a period like 30 seconds on 1 minute, depending on your configuration. So you can, within 1 minute, you can still reuse it, right? Another popular approach is counter-based OTP. So the initial state, instead of let time, we replace it with an incrementing counter. So the initial state, the client and the server has both the shared secret and some kind of counter, right? So again, we use a message authentication code, produce an OTP, and the client then increments this counter, so it's different next time. Send it to the server does the same thing, and it can verify the OTP. Now, it's self-contained, one way. User experience is very similar to password. You just input it in the password field. Again, the problem is requires both parties to keep the counter in sync, right? And it's very hard to achieve without the feedback loop. So what I mean is like, this works well in very good case, but for example, what if in a bad case? So now the user and the server, they're both at counter number 3, right? So the user produced an OTP, but when the user was typing the OTP, it made a typo. So it typed something incorrect, right? So, but the user increments the counter regardless. So it produces OTP, the counter was incremented. But the server couldn't validate the OTP without, because there was a typo on it. So next time user gets a failure, right? User retries, but this time it fails because user now is at counter 4, but the server is at counter 3. So verifiers don't usually only increment the counter on successful verification and not on failed, because if they did it on every verification, then it opens a possibility to a denial of service attack where I can just keep typing gibberish to the server, right, and increase its counter in perpetuity. So what the server can do in this case? It can do like a counter synchronization schema. What it basically means, instead of producing one OTP, the server kind of like produces like a window of potential OTPs within like counter 1, 2, 3, 4, 5, like within like a range. And when the user actually sends an OTP, it can like verify each one of them and then detect that, okay, that what the user sent is actually matching the counter number 4. So it's more likely that the user is the counter number 4, and then the server can remember that and use it next time. So basically, in this case, the verifier can resync with the client within a certain window, but it's still kind of really fragile, because if you're out of the window, you're done. And like we can do like challenge-based OTP. So again, no shared state between besides the shared secret in this case. And what server can do can just like send a random challenge to the user. And this is okay for a text-based info. It can present something on a screen, right? So the user can actually use that challenge to generate an OTP and send a response back, and server, knowing the channel, can recalculate the same OTP. So this is kind of like much better, because now there is no state to keep in sync, and it's actually a truly true OTP, because if we ensure that the server keeps sending a unique challenge every time, the OTP will be truly unique and one time used, right? So it's always in sync and true OTP, assuming unique challenge. But it's not really perfect for multi-user systems. And I'll just explain in a bit why. So let's go back to our OTP setup phase. So this is how it works. We take a shared secret, and basically user has it and the server has it. Again, if we go back to managing a large infrastructural fleet, we have a group of SREs, right? So it means like all these users will have all these shared secrets to provision to the server, right? But the problem here is, because they're SREs, they usually have privileged access. And if you log in, you have like this root access. And what does it in practice mean? If you have root access, you can read all these secrets, right? So, and the problem here is not everyone from this group can read any secret from here, because they just have root access. It's very hard to protect a certain resource from root on Linux. So in some ways, it's even worse than a password now, like every OTP, because like at least with the password, if I'm a malicious intruder, right? So like, or malicious insider, sorry, I steal the shadow file, I'll still have to do the offline attacks like brute forcing or dictionary attacks. Now, if I want to impersonate someone else, I can just steal their seed and like use it as a civil and log in as them very easily. Clear so far? So what can we do better, right? Better than OTP. So let's like zoom out and actually revise what we want to do. So we have this text-based interface. So we want a text-based OTP protocol with reduced risk of password leak, right? And the interactions within the protocol should be possible via simple text exchange. We don't want to depend on state synchronization between the client and the verifier. Likely, like challenge response protocol is the best here. We need a relatively short text challenge. So like, why relatively? It doesn't have to be super short, but it's presented on the screen to the user. User doesn't have to type it, but the user has to really easy, like either like select and copy paste it, or if it's like even an image screen, it can like modern Mac can easily like OCR this. So it's not a problem that it's if it's long-ish, but it shouldn't be like huge, you know, like 256 bytes. And we need and here is we need a really short text response because we only have the keyboard interface. So users should be able to relatively easy to type it. I have to respond to the challenge by typing something in worst case, right? And ideally, we want to have that legitimate users cannot easily impersonate each other, as we discussed in the last slide. So most of these, besides the last one, is satisfied by a simple challenge response OTP, right? But what we can do about the last one. What if we replace the HMAC seed or MAC seed with public key cryptography, right? So the setup now looks like this. So we don't have the shared secret anymore. Instead, the user has a private key, and the server has a corresponding public key. Now it becomes much better, right? Because the server can use the public key to verify the user, and the server needs to just ensure that the user possesses a private part. But if I'm a legitimate insider, I can steal everyone else's public keys, but I cannot recompute their private keys, so I cannot easily impersonate, right? So seems great, and we can even take it one step further. We actually don't need that setup phase if we use SSH. We already have it. So if you have standard SSH configuration, you already have this. So users have their private SSH keys, and the server has their public counterparts in the authorized key files, right? So now the whole problem just boils down to, can we just reuse SSH keys for OTP access over text-based interface? So how could we do it? We can do it naively, relatively, right? So what we can do is the server can present a challenge, some random number, anything, right? And the user can just sign it with a private key, right? So the server can then verify that signature, and the server can have reasonable assumption that the user possesses a private key because it was able to sign the challenge. The good thing about this is this random challenge can be arbitrarily small. You can send literally 1 byte, and it still would be reasonably good. The bad thing about that, you can definitely not use RSA for that. You have to use elliptic curve cryptography because it produces the smaller signatures. But even with reasonably secure ECDSA 256 or ED 25519, the signature will be at least 64 bytes. So the user would need to type 64 characters as a response, right? So not that great. Yeah, I mean, there are you can find papers online for cryptographic signatures, short cryptographic signatures that produce 20 bytes. Still a lot. And we're not sure if you want to use non-standard cryptography in a very important authentication system. So we still want to stick to what modern standards recommend, right? What if we do a different type of proof to the server that a user owns a private key? What if we flip it down to elliptic curve Diffie-Hellman? So if you know crypto, elliptic curve Diffie-Hellman is usually used as a protocol for secret sharing, so to computing the shared secret between the parties. But we can actually flip it in a way that we can flip it into a proof that one party owns a private key. So in this case, as the server, the verifier, can generate just a random public-private key pair. So random, not connected to anything. And it presents the public key as a challenge to the user, totally random one time. Now, having this and assuming we had the setup phase within SSH, both parties can compute the same shared secret, right? So the user will compute the shared secret using this challenge, like a public challenge, and its own private key, SSH private key in this case. And the server can also compute the same shared secret using user's pre-configured public key from authorized key file, and the private part of the challenge is just generated. And then basically, because it's a one-time secret, you don't have to do anything as well. Here, you can just, the user needs to prove to the server the user arrived to the same secret as the server, so it can be just like disclose the secret. And in this case, the user doesn't even have to disclose the whole secret. Like, first 8 bytes would be enough for reasonable security, right? So like because it's a one-time password, the attacker has like only one chance to guess the correct answer. So 8 bytes should give like a negligible chance of an attacker to arrive to the same OTP. So we can actually trim it before sending. And in this case, well, the challenge becomes small. So the public key could be, for ECDSA, it's usually 64 bytes, but it can be compressed to 32 bytes. And for ED25519, it is actually only 32 bytes. And again, it's longer than previously, but this is a challenge. So users don't have to type it. It's just presented on the screen. So it's short enough to be presented on the screen so users can copy-paste it. And then, in this case, the OTP itself can be arbitrarily small. So we can send only the first byte, first 2 bytes. So depending on the security level we want to achieve, we can negotiate. So let's say 8 bytes is enough. So we can trim it to 8 bytes and the verifier will have sufficient confidence that the user computed the same shared secret. And the only problem here, this is all binary exchange, right? So we need to turn it into a text. So we just slam base64 on top. Base64 slightly increases the length of the data. It's like 35 to 40%. So the challenge becomes like 45 byte, which is still manageable, and the OTP can be still quite small. So if you use 8 bytes, then later in the examples you would see like it turns into 11 or 12. So this is what we did. We kind of use this schema as an OTP authentication for emergency access. Now we know what we want to do. The question is how we're going to do it. And in Linux, this is where I wanted to reintroduce to a subsystem called PAM, pluggable authentication modules. Anyone here worked with PAM previously? Yeah. So what is Linux PAM? So basically, you have a group of applications which need to perform different authentication. Couple of examples: SSH daemon performs authentication of users. Login program, which is actually the one that is responsible for accepting a password from a serial console or from a monitor, right? SU program, when you want to elevate privileges or change to another user. And passwd, for example, is a program to change the password. They're all basically PAM-aware applications. And why I say PAM-aware, all of them use the Linux PAM subsystem. And these applications have, so it's not kind of like secret, transparent feature of the operating Linux kernel itself. It's a framework that Linux uses. But so the application has to be PAM-aware. They need to explicitly talk to PAM subsystem to do their authentication things. But luckily, all of the standard Linux tools are coded to use PAM. So you can reasonably accept that standard utilities use PAM. And the whole Linux PAM, and in practice, it means they just link to libpam-so, which does the authentication on the application's behalf. And the PAM framework itself have different 4 types of modules that you can extend it with. So it has an authentication module, an account module, a session, and a password module. We're primarily interested in authentication modules, the modules which implement a particular authentication scheme. So this is what we need to implement our protocol. Account modules are basically which perform additional steps depending on the way how you want to configure the systems. For example, if you want to have a policy let's say that if you're in the SRE group, you automatically get sudo access by getting into sudo group. You can encode this into the account module. So at this point, when the account modules are called, authentication already happened. So you have like the entity of the authenticated user, and then you can perform additional system actions to grant them more privileges, for example. Session modules are usually used for when someone logins and logs out the system, so they kind of record the act of logging in and logging out. They're mostly used for logging and audit purposes. And the password module, even though it's called password, it's actually not to verify password, but to change password. So like passwd uses a password module, so if a user wants to change their credential, the credential needs to have a supporting password module. And one of the typical example which implements everything is a PAM Unix module, which is basically what you read in a textbook how Linux authentication works. So PAM Unix module actually stores password hashes in the etc shadow file, right? Users in the etc passwd file. So it kind of maintains a like offline on-machine password database. And obviously, all of this is configured by configuration files. So you have different locations in the system. So this is like admin version, and you have per service configuration files. You have a distribution provided configuration, and like common configuration. So let's actually see a very toy example of a simplest password module. So this is a fully self-contained module. When you get these slides, you can copy-paste it into a file, and it works as is. So, and the logic here is simple. I call it an evil PAM module, and the main logic is here. So if the logged-in user has user ID as backdoor, we just allow it to access, right? And if not, we return authentication error. So this is kind of like a very simple example. So if you copy-paste this code into a file and compile it, you will get a full-featured, simple PAM module. Now, for it to work, to demonstrate how it works, I will probably also need to add a backdoor user into the system, because even though my PAM module will authenticate, if the user does not exist on my system, later modules will fail and the whole thing will fail. So like we'll ensure that the user is there just for demonstrative purposes. So now that we have the module, we need to configure our PAM system to use it. And I kind of like encapsulate it in this like scary set command, but what it basically does is it modifies the etc pamd login file. And the nice things about like PAM, you can configure policies per service. So for example, by modifying etc pamd login file, I'm only enabling this module for the login that is running on the serial console, but not for SSH, right? So you can have per application policies. And what this set does is I'm searching for a string called include common auth, and I'm inserting an entry in between called auth success to ignore and pass to my PAM module. So yeah, in the result, what I want to achieve is something like this in my PAM configuration file. So I have like 4 items here, and that means like I'm using like authentication modules here. So the path to my SO module is quite easy. It's where it's located, so PAM system can load and execute it, right? What the success to and default ignore means. So this is my evil module. What I want is, if somebody logs in as not backdoor, I want the system to work as is, right? But if I'm backdoor, I want the system to actually like let me in. So if I'm a non-backdoor user, my PAM module will return the authentication failure. But what that default ignore means that I'm ignoring the failure and I'm just continuing executing further. So if I'm logging in as like regular user, the control will just jump to the next rule, which is basically the PAM Unix module. So it will just perform the standard Unix authentication. It will request a password and let the user log in if the password is correct, or fail if the password is not correct. But in the success, if I return success, right, the two means jump 2 items. So, and here I jump the next one and the next one, and I'm jumping to the PAM permit module, which is a dummy module that just allows everything in. Cool? So here is how it would look in the example. So I'm logging in through a serial console here. And by the way, if you have watched my previous presentation, I have these demos embedded in slides, but everything was pasted from a real terminal, so it's kind of a real demo, okay? Yeah, so like let's say I'm not aware that I have a backdoor PAM module, so I'm just logging as myself. So the system will ask me for a password. I can type something in either login, or if I type gibberish, it will detect that the password is wrong and login is incorrect. But if I basically just type a name as backdoor, I'll immediately get a login prompt, right? Because I have a backdoor user on my system. Now, this is like a simple evil example. Now, with sshlogin, the configuration is quite similar. So basically, we use the same modifications. And this is, we still use ignore. And it's not just because we're evil. Like initially, when we're trying this out, we want to still have a reasonable fallback because it's a new thing, right? We want to encourage everyone to use the new OTP schema, but as a backup, because I'm not an ideal software developer, I can write bugs, the users can still log into the system via the old way. So you can still use the same approach. And here you can also pass the parameters. So one is to your PAM module. So one of the parameters is authorized key file. And you notice if you ever configured your SSHD server, it has the same kind of configuration string as a typical SSHD server. So what it means, like search for authorized key files in a user's directory. So %u will be substituted for the actual user's home directory. And this is where like the minimal response length that we kind of want. I think this is an error. I wanted to demonstrate on 8. 16 is probably too long, but like this is the minimum OTP that the server will accept, and it will not accept less than that because we're trimming it, right? And in this case, I also need to ensure that my SSH public key is actually provisioned in the authorized key file. So like this was a clean test machine. Usually it's already there because you have SSH access to the system. So the way how it works now, the first screen is basically my serial console access, and this is my client laptop that I use to access production. So the way how it works is I type my username, and instead of the password request now, my PAM module is being invoked, and the server presents me a challenge. So this is like this base64 encoded public key, which I can, if I'm on a serial console, I can easily like select and copy paste it. Even if it's a real screen, like macOS can really well like OCR it. So like there is no, I don't need to retype every character, so it's quite manageable. So what I do now on my client machine, I launch the response utility, and basically what I provide is a parameter, the host name where I'm trying to log in. It's not a security feature, just for sanity checks. Then I provide the path to my SSH private key file. I want to generate a response length 8, because in this test machine I can... Okay, I'll finish that later. So in this case, I want to generate a response of 8, and I pass the passed-in challenge, right? So you should have your SSH private key password protected. If it is, the tool will ask you for a password. You enter it, and then it will generate a response. And you see response is quite short. It looks like a very small one-time password. Here, it's 8 bytes, it's 12 characters. I can reasonably type it in back, and I will be authenticated and get into my machine. Cool. But what about like hardware keys and 2FA? Because when we adopted like hardware keys for SSH, we were considering between two approaches, like FIDO2 or PIV. FIDO2 is like more easy to get started with, but it has drawbacks. It has like it's more easy to start with because it has native OpenSSH supports. It's represented as a special SK key type. The downsides are it requires recent OpenSSH version. For example, if you use the same approach on some kind of embedded device, it won't work because, well, it might have an older OpenSSH. The problem is for the client. So if you're on macOS as a client, this support is disabled on native macOS implementation, so you have to install your own SSH from brew or something like that. And it's very hard to ensure the proper 2FA. You cannot tell from the key itself if the client uses a PIN to protect the key or not. And the problem for our use case is FIDO2 does not support ECDH for the key, only SSH signatures, specifically for SSH protocol. Now, PIV keys is a little bit better because they can be used with any OpenSSH version. So like from an OpenSSH perspective, it doesn't matter even if you use hardware, software key, it doesn't care. And on the client side, it only requires PKCS module, which is very old and available everywhere. And it's kind of like not like I made this example based on YubiKeys because we use YubiKeys, but it's not kind of limited to YubiKeys. Kind of like any reasonable smart card supports some kind of PKCS 11 interface. The nice thing, at least on YubiKey, with PIV key, you can generate a proof that the private key is PIN protected. So you get proper 2FA here. So for example, during our provisioning process, when we provision users' public keys, we verify that proof. So like users can only provision their public keys to access production if they are PIN protected. So like we enforce 2FA in this way. And the nice thing about the PIV itself supports ECDH, right? So let's see how it's different PIV key looks from the software key. I will not show you the server part. The server part is exactly the same. On the client part is basically, instead of just providing a path to your private key file, you can provide a special string called PIV, and SSH login response will go to your YubiKey and try to use that to provide to generate a one-time password. And here it will most likely ask you for a PIN for the key, and once you input the PIN, it will generate you a response that you can type in. So now we turned into our text-based authentication with like hardware-based full 2FA implementation. One thing I wanted to also show that this kind of like still has poorish user experience. Like when we originally deployed, we had like the SRE group, which is rarely uses emergency access to access the servers. Most of the time it works, but we have a dedicated infrastructure operations group whose primary task is to recover broken machines, and they do it like day after day. So like they complain that like running this command line tool is like really, really exhausting compared to the thing that they had before, the password. Like, so nobody cares that there's better security. Previously, like, oh, I know the password, I can keep typing like every 30 seconds and it works fast, instead of like I do like copy paste and moving forward and everything. So how do we solve that? Do we have better security or easy to use flow? Well, we can try to do both, right? So it's a little bit meme time, and we can piggyback on the shoulders of giants, like who has the best user experience? Can you guess? Microsoft in 1997. Remember, who knows this item, right? It's called Clippy, right? I tried to improve their workflow based on Clippy. Remember that Clippy helpfully said, like, it looks like you're trying to do X. Why don't I just do stuff for you? Like AI from 1997. So how would you implement it? So again, this is our typical setup. So We, by default, still use some kind of SSH, but through emergency out-of-band network, but to the remote machine, right? And the way how user interacts with the local SSH client is simple. It's via standard input and output. So the Clippy program is actually is implemented on the client side, and what it does, it kind of intercepts the user standard in and output and tries to detect the challenge when the remote side requests the challenge. So in practice, how it looks from the client's perspective, again, this is my client machine. For example, if I use SSH some out-of-band device, instead of this, what I would be just running sshlogin Clippy. I'm using the same command. Internally, the Clippy program calls SSH, but it kind of wraps the standard input and output. So I'm still like, seems to have like an SSH, but as soon as I try to log in, I type Ignat, for example, I get the typical challenge from the server, but because I intercept the output on the client side, I color code it in a different color, so my Clippy inserts, detects it and says like, hey, looks like you need to generate a response for host dev, so it parts the host name and it parts the challenge correctly, right? And all the user has to do is like no copy pasting, hit any key, and also if you're talking to YubiKey, you need to assert physical presence, you need to touch it. And even the pin is now cached here. When users configure their Clippy, they kind of put the pin in the environment variable. So they just like literally hit any keyboard key and confirm the YubiKey. So, and they don't have to paste anything. So Clippy, because it also controls the standard output, it goes to your YubiKey, generates a response, and types it in itself. So all you get is like login prompt immediately. So you can just, with 2 key presses, you can get into any system within like reasonable time with a reasonably secure protocol. Cool. I guess this is what I wanted to present today. Some conclusions. Definitely consider an authentication scheme that's used for emergency access during your security reviews. Make sure it's not the weakest link. Public key-based OTPs can offer superior manageability, I think, compared to shared secret standard-based OTPs. Look into Linux PAM and learn it. Linux PAM framework offers centralized and configurable authentication for Linux systems. If you're writing Linux software that needs authentication, consider it making PAM aware. And SSH login can easily reuse existing provisioned SSH credentials for generating secure OTPs for emergency authentication. Now, here are some links for documentation about PAM, the man pages, and the open source project itself. You can go and it has like many existing real world and toy PAM modules that you can investigate and understand how you can do various things with PAM. The third item is probably even more embarrassing than this. So my plan was to open source the whole thing by this presentation. Unfortunately, I got stuck a little bit in the company procedures. So, but I plan to do it by end of this month. So keep an eye on Cloudflare's GitHub. So soon it will be there. So I will add it. And thank you very much. And I think we have a little bit time for questions. Questions? Concerns?
The concern is how vulnerable our software is now seeing this working with IoT devices and off-band networks and whatnot isn't really...
Well, it's always been a concern, and I think the only way to fully address it is taking control of your software. Like for BMC, there is an open BMC project, which if you get proper vendor support, you can kind of like at least roll your own, and you can at least fix known things. But yeah. But there is kind of no other way, right? So like you cannot send, if you manage a network like Cloudflare, you cannot send engineers to data centers every time stuff happens. Anything else? Cool. Thank you. I'll just put this up and pretend it's not me, okay?